Today's lecture provides an introduction to multiple linear regression. And so after this lecture, you'll be introduced to linear algebra and be able to estimate a simple linear regression model using matrix notation. You'll also be capable of estimating a multiple linear regression model, as well as in assessing the underlying assumptions that apply to any of the family of regression models that we'll be talking about. Okay. And so as a starting point, we'll walk through a matrix or linear algebra approach to simple linear regression. We'll then expand that to a discussion of estimating multiple linear regression models. And so multiple in this case means that we have more than one predictor or X variable, and we'll detail some of the model estimation issues that are germane to that end, as well as work through an in-class exercise using the same data we previously introduced that relates to noise data generated by vehicles contacting pavement rumble strips. And so assignment 3 has been posted. It's due midnight this Sunday. And then on Monday, we'll have a review session in advance of Wednesday's midterm exam, which will be take home in nature. It'll come out at the start of our class period at 8:30 and be due at close of business at 5 p.m. So more details will be forthcoming there, but just to give you a sense of what will be coming up in the subsequent weeks. Okay. And so as a starting point, you're all recalling the linear regression model that we've talked about. And in the case of a simple linear regression with just a single predictor variable, we know that we can relate our dependent variable of interest, y, which is unique to an individual observation, which was subscript as I, is a function of our intercept term plus our slope times some independent or predictor or regressor variable of interest, which again is unique to individual or observation I. And since this relationship is stochastic and not deterministic, this collection of terms will give us a general estimate of y, but we'll tend to see some variability above or below that predicted value based upon important unobserved factors that we aren't able to capture directly in our model, okay? And so in matrix notation, we can rewrite this equation as shown here. And so anytime you see bold letters, that's generally indicative of the fact that we're working with matrices here. And so you'll notice the same general form, y is equal to x times beta plus epsilon. The reason that we've swapped x and beta in this case relates back to our operation rules for linear algebra. And so as we'll see for each of these constituent terms, y is a column vector. So in the example we've worked to up to this point, that would be the noise level experienced from location 1 to n, where n was 12 in our case. Our x vector, so in our case, x characterizes the depth of the rumble strips in the pavement measured in inches. And this column of ones is reflective of our constant term. So as we multiply matrix x times beta, we would have beta naught times 1 plus beta 1 times x that corresponds to that individual observation. For each of our observations, again, up to a sample size of n. And then the error term that we're adding on here is just a column vector that describes the noise or uncertainty or other randomness that results in variation from just the y equals x times beta term, okay? And so as we look at this, again, in matrix notation, our general setup is as shown here. And so interestingly, our approach in linear algebra is similar to what we had done previously when we worked through the least squares normal equations, just using some simple algebra. And it turns out that in our consequence, we're again minimizing the sum of the squared error terms here, which again are representative by epsilon here. And so we square that quantity, and in our circumstance, what that means is we're taking the transpose of that column vector times the vector itself. And so we're minimizing that quantity, which in long form is just equal to y minus x times beta. So basically rearranging this in terms of our error term, and then that error term squared is what we're aiming to minimize. And so interestingly, As we work through that process, we'll find that the least squares estimator is denoted as x prime x inverse x prime y. And that is an equation set that you should become familiar with, because we'll find that this is the same solution as we expand beyond one to multiple predictor variables. Our beta hat matrix is always going to be equal to x prime x inverse x prime y. Okay. And so continuing on here, just working through some nomenclature and connecting this to our least squares normal equations. So that x prime x vector, as illustrated here, when we work that out in long form, we're simply multiplying a row of ones times a column of ones and summing those up. And so the top left element here is just going to end up being our sample size, n. The diagonal elements in positions B and C in this matrix are just the sum of our x terms. And then in cell D, we simply have each of these respective x variables squared, and we're summing that across our n respective observations. And so these terms should be familiar if you think back to the equations that were introduced last time for SXX and SXY. And when we invert that matrix, here you can hopefully follow along and recall from linear algebra, we're taking 1 over a times d from our initial system of equations here. So n times the summation of the xi squares, minus b times c, which in this case, we've just got x1, then that quantity squared. And then when we take the inverse of that matrix, we're swapping the locations of A and D in this 2 by 2, and then we're replacing B and C by simply negative B and negative C respectively, okay? And you'll notice then as an alternate formulation here, ignoring this first n, you'll notice the other terms in this equation are basically similar to the SXX, or the total sum of squares for x that we calculated previously. So we would have xi squared, we would sum that across all of our observations, we would subtract the summation of the xi's quantity squared divided by n. And so all we've done here is basically multiplied both sides of that equation by n. So there was previously an n in the denominator here that's gone away. And then the first term is multiplied by n. And so we can think of this essentially as n times SXX with all other variables as previously defined, okay? And then lastly, x prime y. As you can tell here, y being just a column vector, we'll end up with a resulting vector that's 1 column by 2 rows. And the top element there will just be the summation of our y variable, and the second element is going to be the summation of x times y for each of our respective pairs of observations, summed across that entire sample, okay? And so lastly then, our beta hat matrix is simply going to be the product of those matrices x prime x inverse times x prime y. All right, and so the easiest way to demonstrate this is likely to work through an example problem. And so we'll return now to our pavement and rumble strip noise data set. Previously, we had regressed our peak noise level in decibels against our rumble strip depth in inches. The other variable we've not worked with up to this point is the type of pavement. And so here we'll either have a hot mix asphalt or a chip seal that's been introduced. And so a chip seal, for those who are unfamiliar, is basically a pavement surface treatment, which can potentially increase the noise levels given the aggregates that are included there and placed on top of the pavement to address any pavement maintenance related issues. And so we can basically take this variable, and so you'll notice here it's nominal in nature. There are no numbers ascribed to this. And so we're arbitrarily going to create a variable x2, which will set equal to 0 for the pavements that are HMA and equal to 1 for the pavements that are chip seal. And so as we change that variable from 0 to 1, our resulting parameter estimate would basically tell us what the change in noise level would be for a chip seal pavement as compared to an HMA pavement, okay? And so just working through the preceding setup we had with respect to the linear algebra, Here we have our vector x prime times x. And so working through the math here, our sample size n, or 12, is what we see in cell A. B and C are just the summation of our x's, and so 5.39. And element D is the summation of our x squareds, and so that's 2.5751 in our case. Inverting that matrix, again, 1 divided by A times D, so 12 times 2.5751, minus B times C, which is just 5.39 squared. And then all we've done here is swapped A and D and replaced B and C with negative B and C. And so that gives us a final matrix for x prime x inverse as shown here. Likewise, x prime y is calculated as shown here. So the top element is just the summation of our corresponding peak noise measurements. And the bottom element is just the sum of the cross products of x times y, in our case, rumble strip depth times corresponding noise measurements. And so in order to solve for our parameter estimates of interest, we're just taking those matrices x prime x inverse times x prime y. And at the end of the day, that gives us a result that is a matrix, a column matrix with 2 rows. And so we'll find the exact same solution we had seen with the least squared normal equations. Our intercept term is 68.99 decibels, and we see a slope of 26.66 for a 1-inch increase in rumble strip depth. Okay, so identical to what we had seen previously. Now we can take this same approach that we've been working through with respect to linear algebra, and we can expand this to multiple linear regression, where we're relating our noise level, for example, to 2 different variables of interest, and we can go well beyond 2 as an example here. And so the setup and the structure here is very similar to what we saw in the simple linear regression case, with the exception that now we have x1 sub I, x sub 2i, and so forth, all the way up to variable x sub k, where k is the number of regressors in our model. And so basically we have 2 portions of this equation, as we had in the simple linear regression case. The portion highlighted in blue here is essentially deterministic. So here we're capturing or trying to represent known relationships between, say, pavement noise levels and our various characteristics that summarize those pavement systems, including the rumble strip depth and pavement type. And we also have a stochastic or random portion, which represents what we don't know. And so this could include any noise or uncertainty or variability beyond what's represented by this deterministic portion. And that could include measurement error. It could include important variables that were left out of the equation, or just random error in noise ultimately. Okay. And so when we think about this, the setup's generally the same. So these matrices you see down at the bottom are virtually identical. The only difference here is that our beta matrix now ranges beyond beta 1 all the way to beta k, where again, k is the number of regressors or independent variables, and that will correspond to the number of columns here that you see ranging from variable x1 to x2 all the way up to xk, for example. Okay. And as opposed to looking at this as a nice simple 2-dimensional line graph, in this case, we're actually estimating a planar surface here, because we're assuming that x1 and x2 each have a linear relationship with y. And so depending upon from which perspective we're looking at the data here, we can represent this information in several different ways from the way that we're ultimately slicing that planar surface. Now, once we get beyond 3 dimensions, it becomes more challenging. So as we expand this to 3 or more predictor variables, we still maintain the ability to look at each of these in a 2-dimensional space, but we'll find that it's difficult to simultaneously represent the full set of relationships and effects here. Okay. And so as in the case of simple linear regression, we can work through our least squares normal equations. And so here we basically just see a system of equations which can continue growing as we increase the number of x variables in our data set. And we can basically solve that system of equations. And if we do so using linear algebra and matrix notation as had been outlined previously, we end up with the same solution that beta matrix is equal to x prime x inverse x prime y. Okay? And so we can take the resulting regression model, and as before, we can represent this as an ANOVA table. In the case of simple linear regression, that ANOVA test will simply tell us whether there's a linear relationship between y and our one predictor variable of interest x. In the case of multiple linear regression, interpretation is slightly different. So in this case, our null hypothesis is essentially that all of our parameters are simultaneously equal to 0. And so we're using our F statistic to evaluate whether or not that is true. And if we reject that null, that would suggest that there's at least one parameter that's significantly different from 0, and consequently, we could use a series of t-tests then to determine which of those is ultimately non-zero in nature. And so the actual setup here, though, is essentially identical to what we had talked about previously. Our total sum of squares is equal to our regression sum of squares plus our error sum of squares. And the long form notation is as indicated here. So the regression piece is simply measuring the square distance of the predicted value of each observation versus the mean value of the sample. And the error component is the difference between each of those individual data points and what's been predicted by our best fit line. Okay. And relatedly, we can estimate the variance of our regression equation. And so if we wanted to determine the variability of our y hat, our prediction, that's simply equal to the mean squared error. And so to get there, we take our error sum of squares, which was presented previously. So just squaring the difference between each observation and what's predicted by our best fit line, dividing that by our corresponding degrees of freedom, which in our case is our sample size n divided by the number of parameters. And so in this case, we would include our constant term as one of the parameters. So just to refresh everyone's memory, p is equal to k plus 1. So we include the constant term in some of our calculations and not others. And in this case, we would take our sample size minus the number of parameters to give us our estimate of the variance for our regression equation. And so from here, we can conduct a series of t-tests. And as noted previously, in each of these cases, our null hypothesis is basically that each of those parameters or slopes, for example, is equal to 0 against the alternative hypothesis that the slope is non-zero, which would suggest there is an effect between, or at least a relationship between that specific x and y, okay? And so we evaluate those hypotheses using a t-test. And so that t-test is simply calculated as our corresponding parameter estimate, so our beta, which was estimated, divided by its associated standard error, okay? And that standard error is simply equal to our variance estimate. And so sigma hat squared, as you'll recall from the preceding slide, is just our mean squared error from our ANOVA table, times the corresponding element of our variance covariance matrix. And so this is basically a matrix which we can construct that would relate the variance of each of our predictor variables of interest as well as the covariance between those respective predictors. And so we won't delve in great detail into the calculation of this, but this is essentially what the software program will be doing in aiming to estimate this. And so the mean squared error is going to be the same regardless of what parameter we're estimating. And depending if we're looking at variable beta naught or beta 1 or beta 2, whatever the case may be, we would go to the corresponding diagonal element of that matrix to calculate the standard error, okay? R squared will return to again. Now, as you'll recall previously, that's simply capturing the proportion of our total variability that can be explained by our regression equation. And so that can be expressed either as the ratio of our regression sum of squares to our total sum of squares, or simply the complement 1 minus our error sum of squares divided by our total sum of squares, okay? Now, interestingly, what we'll tend to see is that as we add variables to our model, R squared is always going to increase. And so as a consequence of that, we're somewhat concerned with adding variables to our model that don't add any meaningful contribution or do a sufficient job of explaining the variability in our dependent variable y. And so consequently, what we do here is we make an adjustment that penalizes R squared based upon the number of parameters that are added to the model. And the way that we do that is we take the ratio of SSE divided by n minus p, where we have our sample size minus, again, our number of parameters, inclusive of the constant term, divided by our total sum of squares over n minus 1, where n is, again, our sample size. And so what we're doing here, in essence, is we're introducing a penalty for each variable that's included. And so we would need to see a sufficiently large reduction in our error sum of squares, or alternately, a sufficiently large increase in our regression sum of squares to overcome that penalty that's imposed by subtracting 1 for each additional parameter that's added to that model, okay? And so interpretation is straightforward here. We simply compare those values of adjusted R squared, and the higher that value is, the better fit the model is. All right. Okay. And so returning now to our pavement analysis using the noise data that was introduced previously, we're going to work through. Now I've simply run this in Excel. We'll demonstrate this right now. Actually, we'll take a quick break from the lecture. And so now you see that our data has been opened in Excel. And so we've taken the information that was summarized in the PowerPoint slides. We have X1, which is our rumble strip depth in inches. We have X2, which is a binary indicator variable equal to 1 for chip seal or 0 for HMA pavements. And Y is our peak noise level in decibels. I'm going to go up to data and use our data analysis tools here. I'm going to select regression. And then from here, we're simply highlighting our Y variable, our X variables collectively. I've indicated that the top row here includes labels. I've specified a confidence level of 95%. I'm outputting the results to a new worksheet, and then I'm saving our residuals, our standardized residuals. And so this is basically each individual residual divided by the square root of our mean squared error, or divided by sigma hat in this case. And then we're going to plot the residuals versus each of our X variables. We're going to plot Y observed and Y predicted against our X's. And we're also going to construct a normal probability plot, and we'll return to each of these points subsequently in the lecture. And so I hit OK. We end up with our results as outputted here. And now I'm going to circle back to the PowerPoint slides to continue through the presentation of these results. Okay, and so pulling it back into our PowerPoint, first of all, the output results here, we see our respective betas. So our intercept term, 68.19, our slope that corresponds to rumble strip depth, 26.71, and the measurement of whether this is a chip seal or HMA pavement. And so we see a 1.5 decibel greater noise level in chip seal relative to HMA. Interestingly, the constant term is relatively similar, although slightly lower in magnitude in this case. And we also see that we have relatively similar results for the effects of noise. So no particular concerns with variables being correlated with one another here. The standard error, which again, this is just simply taking the square root of our mean squared error times the corresponding value from the variance covariance matrix. And our calculated t-statistic is simply our coefficient divided by its corresponding standard error. And so we see those results right here, along with the corresponding p-values, which tell us that our intercept term, as well as our variable that represents the depth of the rumble strips, are both highly significant. So these would be significant at alphas of less than 0.001 and even less than that. The difference between HMA and chip seal pavements is not significant at 95% confidence, and so we would fail to reject the null in that case. And we're also given upper and lower confidence limits on each of these coefficients. And so as we had seen previously for some of our statistical tests, these are basically giving us bounds that would correspond essentially directly to the results of the hypothesis test here. And so in the case of the intercept, this is basically giving us bounds that would indicate how far up and down that value would be shifted if we conducted repeated samples based on the information we have from these 12 observations in this case. Whereas the slopes are basically giving us a range as to the slope of that line. So based upon repeated sampling on our sample, we would expect that 95% of the time, those limits would range from a slope of 16.8 to 36.6 roughly. And then lastly, for the case of the pavement type, you'll notice this is the one case where these bounds actually include 0. And so what that means in effect is that we cannot claim that that effect is significantly different from 0, and that corresponds with the results of our t-test as indicated here. So if, for example, our p-value was less than 0.05 in the case of a 95% confidence level, if we reject the null, this interval over here would not include 0, and if we fail to reject the null, this interval would include 0, as we see in the case of x2, okay? So in addition to the model estimates, we also see our line fit plots, and so this is just showing us both for y and y hat, how those variables relate to x1 and x2 respectively. And so as you'll see here, strong linear relationship for x1, weaker relationship for x2, so not as much of a compelling trend being exhibited there. Our ANOVA results are as shown here. So our sums of squares as calculated noted in the previous slides, our corresponding degrees of freedom. So we have 2 regressors in this case, which leaves 9 degrees of freedom for the error. Our calculated mean squares are then simply our sums of squares divided by the corresponding degrees of freedom. And then our f-test is just the ratio of mean square for the regression over the mean squared error. And its corresponding p-value, again, is highly significant as indicated here, okay? And then the last output that's provided to us are some summary statistics, and that would include R, so just a simple correlation coefficient between our observed and predicted values, R squared, which is calculated based upon the ratio of SSR to SST, and then our adjusted R squared, which penalizes for those additional parameters that have been added to our model, okay? And so that's a relatively quick introduction in terms of how we estimate these models in Excel. One thing we've not talked about up to this point is assessing our underlying regression assumptions, which we have not done in any form yet up to this point. And so just as we had seen with some of the statistical tests outlined previously, there are certain assumptions for applying Student's T, Welch's T, some of the other standard parametric tests that have been introduced, and the same is true for linear regression. And so the first assumption in a linear, emphasis on the term regression model, is simply that y is linearly related to x. In addition, our error terms or our residuals also introduce some additional underlying assumptions. First of all, we assume those errors are uncorrelated with one another. So as we look at the errors that correspond to different observations, we wouldn't expect to see a natural pattern with them. And that would include if we took the values of those errors and compared them to the individual x's, or to our predicted values of y, or to time as an example. Secondly, we assume that those errors have constant variance, or another way of stating that those errors are homoscedastic. And so in that case, this is similar to looking at Student's versus Welch's T. So under Student's T, you'll recall an assumption of constant variance. Likewise, in ANOVA, we assumed the variance was roughly equal across our groups. And so if that assumption were violated, and similarly in the linear regression case, our concern would be that we would be more likely to commit a type 1 or a type 2 error, so basically come to erroneous conclusions given the fact that we have non-constant variance. And then lastly, we also assume those error terms are normally distributed. And so collectively, these 4 assumptions apply to both simple linear regression and multiple linear regression. And the 5th assumption, which applies only to the multiple case, is that our x's are independent of one another, okay? And so that's not true when we have what's referred to as multicollinearity, which we'll circle back to momentarily, okay? And so in assessing these assumptions, the easiest one at the onset is to assess linearity. And the simplest way to do that is just by plotting y versus x. And so we can do this for each of our individual x variables. And what we'll hopefully see, as is illustrated in this figure here, is that we have a consistent decreasing or increasing relationship between y and x when we plot those out, okay? If this were violated, we do have some remedial measures that we could introduce, but this is generally a nice, easy check that we can do even before going in to estimate our respective models, okay? Beyond linearity, each of the other assumptions will generally require us to work with our residuals. And so we've introduced this previously, but when we talk about residuals, these are basically our error terms denoted as E. And so each individual observation has an associated residual, and it's simply equal to the observed value of y minus the predicted value based upon our regression equation, okay? And so residuals are helpful for us because they allow us to check the aforementioned assumptions, principally that those errors are both uncorrelated with one another and have constant variance. And we assess these by using a series of residual plots, okay? So we can plot our residuals versus our predicted values. And what we would hope to see is basically a random shotgun blast where there's no particular trend emerging. So we would be looking to see that these errors are independent. So there's no pattern here. Say we could see consistently decreasing or increasing values, which would suggest that maybe a linear relationship isn't a good assumption. Or we may see that the variability differs significantly as our predicted values get larger or smaller, as the case may be, which would be a violation of our constant variance assumption. We see neither of those concerns in this sample plot. Likewise, we can plot our residuals versus each of our individual x's. And again, in this sample case, we really don't see much of concern here. And we'll return and do the same diagnostics with our sample data set here momentarily. A few example slides, first of all, though, looking at the use of these residual plots. And so we can use them to assess linearity. So in this case, we see our raw plot of y versus x, and then we see our residual plot. And so just to orient you here, our residual is just y minus y hat. And so we're simply taking each of these individual observations and subtracting off its predicted value. Or you can simply think of this as us essentially tilting this axis so that's horizontal here. And so you'll notice that these are essentially analogous to one another. And so whenever you see values that are coming above the line here, that essentially means that we're tending to underpredict with our model. And in cases where the points are falling below that line, as you see here, we're tending to overpredict those values, okay? Now, in this case, it looks like we may have some sort of second order function here because while there does appear to be a relationship, it doesn't look like that's necessarily linear. In contrast, over here, we see what looks to be a nice linear relationship. If we look at the corresponding residual plot, no concerns here, and it seems like our linearity assumption is fine. Continuing on to our variance assumptions. Here we see an issue that arises somewhat commonly, and this is basically referred to as a megaphone shape. And so what we're seeing here is that our variability is tending to increase as x increases or as y hat increases, as the case may be. And this happens occasionally. So let's say we were looking at something like the amount people travel as a function of income, for example. And so lower income households may have less flexibility in how much they travel. And so we may see that those observations tend to fall close to the line, whereas at the higher end of the spectrum, we have a lot more flexibility, and some people may choose to travel quite a bit. Some people may choose to travel quite a bit less. and consequently we may see some sort of relationship, and that's just one example, but there are myriad cases where this could arise within an empirical setting. What we would hope to see instead is something similar to what's illustrated here, where we have relatively constant level of variance across each value of X or against Y hat, as the case may be. We can also check independence, and so we see a few examples here. So there may be some seasonal effects. So if we think about things like maybe travel speeds, and we're measuring travel speeds, let's say from the time that a speed limit feedback sign or a speed feedback sign was introduced. And so maybe we see low speeds immediately after that sign is introduced because drivers tend to be paranoid, for example. But maybe over time they see that if they travel at higher speeds, there's no negative repercussion. And so over time, those speeds may drift back up to where they were initially, for example. Or maybe we're measuring speeds during different time periods of year. And so maybe in the summer and in the warmer months, speeds tend to be higher, and in the winter, they tend to be lower. And so if we're not accounting for that directly as a part of our analysis, and we're taking these measurements at different time periods, we may inadvertently violate the regression assumption of independence here. What we would hope to see instead is similar to what we'd seen in the preceding plot, just a random scatter of plots about that line. Okay. All right. Lastly, assessing normality. We've previously talked about using a chi-square goodness of fit test or a Kolmogorov-Smirnov test. An easy graphical way of assessing normality is using what's referred to as a normal probability plot. And so what we do here basically is we use scaled paper or plots that overlay what our distribution should look like if we assume normality. And we plot our points against that line. And if in fact the data are normally distributed, they would tend to follow a straight line. So as you see right here, what we've basically done is we've scaled our error terms, we've sorted them in ascending order. And so assuming a normal distribution, we would know that 2.5% of our points should be at or below negative 1.96, 2.5% should be above positive 1.96. And we can also determine how likely it is that subsequent observations would occur at various values here. And so what we would hope to see is that these points all fall very close along this line, which generally holds here. You'll notice at the extremes, we do tend to see a bit of a variation there. I don't have particular concerns here because we're generally good until we get out to the very extreme values here. And unfortunately, there's not a cut and dried way of formally evaluating these through a hypothesis test, for example. It's largely experience and look and feel and being used to working with these types of data. So this is a skill set that you'll hopefully acquire over the remainder of the semester. And so if we return to our prior example from the Excel output, we have plots of our residuals versus X1 and X2. Now keep in mind, these are relatively small samples, and so it would be difficult to identify particular concerns here with respect to violating those assumptions. But we don't really see any trends of concern here, and it doesn't appear like we have the megaphone shape or any of those other violations we were concerned with previously. The same is true for X2 here. And then lastly, we'll see the normal probability plot on the bottom. Now, instead of standard normal quantiles from -3 to 3 on the bottom, we basically see the corresponding percentiles, but these are calculated in a similar manner. So we take our observations, sort them in ascending order, and then try to figure out what the corresponding percentile would be based on a standard normal distribution, okay? And again, they're falling relatively close to the line, so we don't have any particular concerns as they relate to normality for our data set. Okay, and so the question then becomes, well, if we do see violations of our assumption, what do we do? And so the short answer is we can transform either our Y variable or our X variable. And so when we conduct transformations, we're basically changing the scale of our variable. And I don't mean we're simply changing from inches to eighths of an inch as we had done during the last lecture. We saw all that did was rescale our parameter estimates. What we're doing instead is we're introducing mathematical operations to either y or x to try to take a relationship that's, for example, either not linear or is not exhibiting constant variance, and we try to fix that mechanically. Now, in doing so, we still want to focus on the analysis of our variables with respect to their individual units of measure. And so when interpreting the results, we basically transform these back and do the opposing operator. And so, for example, if we were to log one of our variables, we could determine the parameter estimates, and then we'd want to exponentiate those results back to determine what the change is on the original unit of measurement. Now, one concern that arises here is we may fix one problem, so we may address a nonlinearity, but that could introduce concerns as to constant variance or vice versa. And so this can turn into an iterative procedure, and the next few slides give a little bit of guidance here. So let's say we plotted y versus x, and I think you'd agree in neither of these cases does a linear relationship look appropriate. In the top figure, we see that y is tending to increase more rapidly as x gets larger, and the converse is true in the bottom plot. And so in either of these cases, it looks like we have some kind of quadratic relationship. And so one solution here would be to try a parabolic transformation. So instead of just regressing y versus x, we could regress y versus x and add an x squared term as well, okay? The next slide, you'll notice very rapid changes in y at small values of x, and then we start to taper off and asymptotically approach some limiting values. And so in this case, the transformation that would be appropriate would be simply to take the inverse of y, as the case may be, and that would take this relationship and generally translate it into something that's closer to linear in effect. And then lastly, and this is probably among our most common, in these cases, we have functions that look to be exponential in nature, and so we could take our y variable and use a log transform in this case to force these nonlinear relationships to be something that's closer to linear, okay? And so it largely becomes an iterative procedure of us transforming, rerunning the analyses, and then rechecking our underlying assumptions, okay? And so some general rules of thumb, when we transform our x variables, that's not going to have any impact on our error terms, interestingly. And so oftentimes that might be the first thing we check is whether we can transform an x and have all of our other assumptions essentially unaffected. If we end up transforming y, that will introduce changes to the distribution of our error terms. And so we would then need to revisit our relationship between those error terms and x as well as y hat, as well as time if there's any temporal effect. And again, just restating that we should always, as a part of these analyses, be comparing our results only on the original units of our dependent variable, okay? A few other related concerns we'll talk through very briefly. Outliers are a concern, and so you're probably somewhat familiar with this. We may have data points that show relationships that are counterintuitive to what we're seeing more broadly. So maybe we've got an extremely large value or an extremely small value that's tending to give disproportionate weight to our slope so that our slope terms are biased upwards or downwards, as the case may be. We can identify this graphically by basically standardizing our residuals. So we simply take each residual and divide by its corresponding standard error, or in this case, the standard deviation of those error terms, which in this case is just sigma hat. And so you may recall we could get sigma hat by just calculating our mean squared error from the ANOVA table and taking its square root. And so in looking at these values, we should see that those generally would fall within plus or minus 2 standard deviations if we get values that are 3 or 4 times larger. So you'll notice the general unit here, this is telling us how far each residual is from the best fit line in terms of standard deviation units. And so values of say 4 and above would be particular concerns because it would be very unlikely we would see that extreme of a value, okay? And values that are significantly larger than that may deserve even greater scrutiny. With that being said, we don't want to get in the habit of just throwing data away because it doesn't happen to fit our model. With the model estimation, we're trying to take a relationship and develop a hypothetical or theoretical model of what's driving that relationship and those trends that we're observing in the data. And so we want to be very careful about rejecting data unless we have a sound reason to do so. With that being said, these outliers could represent anomalies. They could be the result of data collection errors, or they could suggest an area where we maybe need to investigate our data further. So maybe there's some important variable that explains why that particular observation may be looking to be an outlier. But when we account for that other factor, maybe it brings our results more in line. And so we should really tread somewhat carefully when we're trying to assess these potential outliers, okay? More broadly, as we look to build multiple linear regression models, there are a variety of things we should consider when adding or removing variables from our model. And from a big picture perspective, there's at least 3 considerations when we're looking at keeping or removing a variable from our model. And that's whether the variable is statistically significant, whatever our confidence level may be. Secondly, whether it's practically significant. And thirdly, whether or not it's logically defensible. And so statistical significance is straightforward. So generally speaking, you may see some argue if you don't meet the prescribed significance level of 0.05 or 0.01 or whatever the case may be, that you should remove that variable from the model. Now, I would push back a little bit on that. So for example, in our analysis, we were looking at the effects of rumble strip depth. And so while we saw a strong effect here, if we didn't see an effect, I wouldn't say that it would be worth excluding that result from our analysis. But in the write-up, I would emphasize that the key finding was that there was no significant relationship. And that's important because sometimes it's as or more important when we indicate results that we didn't see as to what we would actually see. And that reverts back to a term that's referred to as publication bias, where if we look at the literature, we see a disproportionate number of papers that are focused on results that are quote unquote statistically significant, okay? And just because an effect is not significant doesn't mean that it's not noteworthy and won't be useful to DOTs or other road agencies as an example. Relatedly, just because something's statistically significant, we should ask whether or not there's practical significance. And so in our case, pavement type showed a difference of 1.5 decibels, which isn't particularly large. And while that wasn't statistically significant, it was relatively close. And so had we collected additional data, we may have found a statistically significant result subsequently. But from a fundamental perspective, a 1.5 decibel difference in noises just really doesn't resonate, as the case may be. And then lastly, we want our results to be logically defensible. So if we think about, say, a significance level of 0.05, we're establishing a priori that we're willing to accept 1 out of 20 variables we find to be statistically significant is by mistake in effect, okay? And so consequently, just because a variable is statistically significant, it doesn't necessarily mean that we should include it. It may be reflective of something that truly is important, but we're not actually capturing in our model, or we could have just got unlucky in terms of our sampling strategy. And so it just happened we found an effect that was statistically significant when in fact there's no meaningful relationship between those X and Y variables, okay? Now, I've uploaded a very interesting article that outlines some of the different considerations we should look to when we're conducting statistical research and evaluating and assessing the results of statistical tests and confidence intervals and so forth. And so I would encourage you to read through that in advance of Wednesday's class. Okay. Lastly, a few quick notes on model selection. And so there are at least 2 general approaches to building multiple linear regression models. The first, and the one that I ascribe to generally, is forward selection. So in this case, I basically run every possible simple linear regression model. So I'm looking at individual variables and whether each of those X's has an influence on Y. I'll then take whichever the strongest of those predictors are, and that'll serve as the basis for our model. And I'll keep adding variables that have shown strong predictive power individually and evaluate improvements in our adjusted R-squared. Now, this tends to be somewhat of a laborious process, and sometimes we'll add a variable, add additional variables, and start dropping variables out as well, depending upon what kind of changes we see in the subsequent t-statistics and p-values. But that's a reasonable approach. A second approach is backward selection. And in this case, we basically throw all of our parameters into the model, and we begin eliminating those that are not found to be statistically significant. So as an example, we'd start removing the variables with the highest p-values. We'd evaluate changes in our adjusted R-squared, and we would stop once that value essentially has stabilized. So as we start removing variables, if the adjusted R-squared declines, then we would want to maybe stop at that point prior to that decline beginning to occur. Okay, so either approach is valid. You should perhaps be somewhat more careful with backward selection, because if you throw everything in at once and some of your regression assumptions are violated, it can become more challenging to figure out which of the variables is the culprit there. Whereas with forward selection, we can kind of make that determination as we go. But either case is suitable, and you'll see either one applied with great frequency in the research literature. A few other estimation issues to be concerned with. The first of which is multicollinearity. So if we have two predictor variables that are strongly correlated with one another, those can introduce concerns, and we may end up with biased estimates of what the actual relationship between Y and those correlated X variables are. Or we can also run into a circumstance that's referred to as omitted variable bias. Now, this one's really challenging to diagnose because it's basically telling us that there's an important variable that we don't have data for that explains a lot of the variability in Y. And since we don't have access to that data, and we might not even know this relationship exists, it's tough to diagnose. But one concern here is if that omitted variable is correlated with something else that's included in the model. Because what happens then is that these effects are captured by that other variable, and we may then from that determine that there's a causative relationship when in fact there's not. So these omitted variables can basically wreak havoc with respect to variables that are included in our model and correlated with whatever that omitted variable may be. Okay, so we'll talk about these a little bit more later on in the course. Generally speaking, our best case scenario is if two variables are completely uncorrelated with one another. Now, it's virtually impossible for us to find an R or an R-squared of exactly 0. But if those numbers, if that correlation is sufficiently weak, then we'll basically find these coefficients remain unchanged regardless as to whether or not those two variables are included in our model. Okay? And so back to multicollinearity quickly. So it doesn't necessarily create problems from a predictive standpoint. Mechanically, we can often still estimate the model. We can construct confidence intervals, hypothesis tests, etc. The problem that arises is if you have strong multicollinearity, we tend to see very large sampling variability for the regression coefficients. So what we mean by that is that the standard errors tend to be very large, and we'll run into some examples of this as we work through the course. But if our standard errors are very large, that means our t-statistics will tend to be very small, and consequently, we're significantly more likely to commit a type 2 error or basically fail to identify a meaningful relationship between X and Y when one actually exists. Okay? There are also difficulties in interpreting regression coefficients. And so as an example, my master's research focused on the safety impacts of horizontal curves that were located near intersections. And we looked at the effects of curve radius and superelevation on crash risk. And since curve radius and superelevation are generally directly related to one another, so from a design standpoint, oftentimes our superelevation rate is selected based on our curve radius or vice versa. we weren't able to find meaningful relationships when those were both included in our model. And so as a consequence, we basically made the decision to include curve radius and not super elevation, while providing some general guidance to designers as to what those super elevation decisions may lead to from a safety perspective. Okay. And in that same circumstance, we were running into situations where we'd actually come up with a counterintuitive sign, because if our two predictor variables are strongly correlated with one another, or if it's correlated with an omitted variable, we could end up with incorrect signs in these instances as well. And so when you see results that are counterintuitive, you do want to think through as to whether or not one of these issues may arise. Okay. And then in some extreme cases, if that relationship is so strong, it may introduce challenges in trying to arrive at our least squares estimates, and we would need very strong correlation in order for that phenomenon to occur. Okay. And so as indicated previously, the big problem with multicollinearity is that it makes our standard errors very large. And so to assess the degree to which this is a problem, this is something we can automate in some of our software estimation programs. We can calculate a variance inflation factor for any parameter of interest. And so all we do in this case is we just basically run a multiple linear regression where we take each of our individual predictors and regress it against all of the other predictors that are included in our model. If that variance inflation factor is very large, and again, this is a subjective term to a degree, but in the literature, you'll see numbers of 5 or 10 as kind of minimum values at which variance inflation is a concern and may be reflective of multicollinearity. And so in those instances, that could flag a variable that may need to be considered more carefully. Okay. And so that gives you a relatively quick introduction to multiple linear regression. We'll circle back and talk about this more in the subsequent lecture. As a reminder, assignment 3 is due on Sunday, and our midterm exam will be a week from Wednesday. So with that, thank you very much.